I would now like to introduce our keynote speaker, Darren. All of you are here today because climate change impacts on your organisation or your area of responsibility. We invited Darren to present the latest in climate knowledge from the Bureau of Meteorology. Darren completed a degree in Meteorology and Oceanography in 2000 at Flinders University before joining the BOM Graduate Meteorologist Training Program in 2001, receiving a graduate diploma in Applied Meteorology and commencing work as a forecasting meteorologist in the South Australian region. I'm going to kill you. So, in 2006, he followed his interest in climate influences and climate change into the South Australian Climate Section, where he is responsible for monitoring climate influences and long-term trends relevant to South Australia. Today, Darren will share with us some of these climate influences and long-term trends. Across the day, we can analyse what these mean for particular sectors and regions. So please, welcome Darren.
So why are we here? So I'm going to do my best to actually leave everyone with absolutely no doubt about the challenges and challenges of climate change and what brings us all here together today. So essentially we've put an awful lot of carbon dioxide in the atmosphere, and as Professor Bursell pointed out, we've done that in a very, very short space of time, geologically speaking. So we've put over 550 billion tonnes of carbon from fossil fuel and cement and chopping down trees have gone into the atmosphere in the last 200 years or so since industrialisation. So what happens to that carbon dioxide? Where does it go? The trees take up some of that carbon dioxide, so they lock up some of that carbon dioxide out of the atmosphere. Roughly about a quarter of it eventually ends up in trees, or soil carbon or other natural processes. The oceans take up some of that carbon dioxide, about another 25, 30, 40%, depending on the time frame you're talking about. But importantly, over centuries to thousands of years, a significant proportion of that carbon dioxide and other greenhouse gases stays in the atmosphere. So around 30 to 50% over centuries to thousands of years. So all of the emissions that we created coming here today, all the emissions we're creating right at the moment, a significant proportion of those are going to be there for centuries and thousands of years in the atmosphere, trapping heat over that time. And I guess the other important point is there's quite significant lags between the greenhouse gas emissions into the atmosphere and the temperature response that we see in the lands and the oceans, and then the consequent response of melting of ice caps and then sea level rise and other issues. So we see these series of lags over decades or even centuries that take time to play out. So if we look at atmospheric carbon dioxide levels as one of the major greenhouse gases over geological time, so that's going back 400,000 years or so, we see that the levels have fluctuated between a fairly narrow band, and that's related to going into and out of ice ages, of around 280 parts per million. And then there's that spike on the right-hand side there that really leaps up, increases by about 40% over a very short period of time geologically, over a space of 200 years. We've seen carbon dioxide levels and other greenhouse gases that we haven't seen for millions of years. So humanity hasn't been around for this before. And I guess just to focus in more on the shorter time frame, what are we doing with our emissions? There's actually not a lot of indication that we're slowing things down at all. The graph on the top right there is actually indicating that's our carbon dioxide emissions into the atmosphere by year over the last few decades. And there was a little bit of a blip downwards there in the global financial crisis a couple of years ago that you can see near the top right there. But there's been actually no sign that that's actually significantly slowed at all. And in fact, we saw the highest annual carbon dioxide emissions occurring in 2011, and the largest increase in emissions ever occurred in 2010. And so yeah, we're seeing continued strong increases in greenhouse gas levels in carbon dioxide, methane and other greenhouse gas levels such that carbon dioxide is now very, very, very close to 400 parts per million in the atmosphere. And those coloured lines you can see on that graph there are actually various intergovernmental panel on climate change greenhouse gas scenarios that were put forward in one of the earlier assessment reports, and basically that indicates our emissions are right at the top of the range of those scenarios that we put forward. So this is the important question: what are those increased greenhouse gas levels doing? Well, we're actually measuring. I could go into the physics. There's a whole lot of direct laboratory. We'll try and get that one out. Lab experiments that have been done since about 1860s, measuring the direct effects of greenhouse gases and how they trap infrared heat. So there's a lot of there's physical experiments. There's all the modelling. We're actually measuring the temperature rises. We are seeing less heat coming back, escaping out to space in satellite measurements. So direct observations of the increasing greenhouse gas effect, trapping heat within the atmosphere and within the Earth's climate system. And we're seeing more heat being measured coming back to the surface as well. So two separate, independent, direct observations telling us that the greenhouse effect is increasing in strength over recent decades. So that's, I'll leave it there in terms of, I won't go into the depths of the science. I don't have time to pull out some of the detail with that. But just to reassure you, there are direct measurements coming from different independent measurement indicators telling us that the greenhouse effect is increasing over the last few decades, as expected. So what kind of effect is that having? Well, basically, per square metre, we're seeing about extra 1.5 watts or so of energy coming back down to the Earth's surface. Now, if you take an area about this size, maybe a little bit bigger, about 1,000 square metres, you stick a standard electric heater over the top of that. That's about the amount of energy that's coming back to the surface. So if you do that over every similar area across the whole Earth's surface, that's about the size of the energy that we're seeing return back to the surface. So it's certainly not insignificant, and it certainly adds up in terms of making the climate system more energetic generally. So where's the heat going? A lot of it's actually being captured in the oceans. So the oceans are about 7/10 of the Earth's surface, and this graph here shows the ocean heat content increasing both over the 0 to 700 metre layer, so surface surface layers of the oceans, and also into the middle layers of the ocean as well. So that's 700 to 2,000 metre level. And the red line there is actually showing, we're actually seeing a lot less of the heat being actually going into heating up the air near the surface. So the ocean's actually taking up a lot of the heat. And it's quite relevant to point out, we're actually seeing record ocean temperatures around Australia right at the moment. And that has regional impacts in terms of changes in rainfall patterns and temperature patterns. But warming on land also certainly does continue. So this is the graph of various international centres who do averages of global temperature that go back to about the 1880s. And there are 4 main centres around the world that do that. They have slightly different methods. They treat the Arctic slightly differently, for instance. But they certainly, as you can see from that graph, end up with very similar results, showing that there's quite a bit of variability year to year. So a lot of the wiggles in the graph there. There are some variations decade to decade, but quite clear that overall rising trend in the last few decades, it's really quite clear across all of those data sets. Now there are some quibbles about what the warmest year on record has been. The Hadley Centre, the Met Office in the UK, argue that 1998 was probably the warmest year on record, but all the other data sets say that 2010 was the hottest year on record. So that variation comes down to how you treat the Arctic and the warming that's going on in the Arctic. 2010 in the majority of those data sets was the warmest year on record. So there's actually no indication that we're seeing any sign of global warming stopping or reversing or anything like that. So Professor Versel mentioned that we are seeing, certainly alluded to some of the material that we're seeing coming through in some of the media. And one of the recent sort of arguments that we've seen come through has been suggesting that global warming has stopped because we're not seeing continued temperature rises globally. Well, they tend to pick on that heavily censored data set, which suggests that perhaps 1998 was the warmest year on record, but if you look across all of the data sets, the indication is more like that 2010 was the warmest year. And another way of looking at this is if you take that raw global temperature data set, you take away all of the natural variability, influences from natural variability that affect that, particularly those year-to-year wiggles that we see in the data set. So things like El Nino La Nina events, so they tend to provide a cooling or warming influence for about a year or so while they're around, as well as changing Australian rainfall patterns. Volcanoes, as we can see in the middle graph there, they have a bit of a cooling influence for a year or two, the really large ones, after those events occur. And there's also some recent work suggesting that if you add up all of the small and moderate volcanic events, they have a significant cooling effect as well. And there's also variations in solar activity. So we see that in the sunspot cycle in the bottom graph there. And there's actually indications that the last 10 years or so, we've actually seen a bit of a cooling, slight cooling from solar activity as well. So what happens if you take the global temperature record, take away all of those influences from natural variability, and that will then leave you the greenhouse gas signal. What do you end up with? Well, you end up with essentially a straight line going up at a steady rate of about 0.2 degrees per decade. So that's what that looks like. That's essentially the greenhouse gas warming signal that we're seeing, and no indication there that we're seeing any slowing down of that warming. So what we are seeing is perhaps a slight slowing in the rate of warming compared to what we saw through the 90s, 80s and 90s. Coming from natural variability. So that natural variability is slowing down the warming a little bit. There's actually no sign at all the greenhouse gas signal has gone away by any means. And so we're continuing to see Australian and South Australian temperatures rising. So that's a graph of South Australian temperatures for the South State as a whole. And while there is year-to-year variability in there, and we can see some cooler years in the last couple of years associated with some La Nina events. So they bring a lot of rain, a lot of cloud. So that's a feature of natural variability that causes the year-to-year wiggles. There is that still there, that steady upwards warming trend. And that's also reflecting in our extreme temperatures as well. So we're certainly, we've been feeling that a bit in the last few months. We are seeing overall for Australia, in that graph in the top left, top there, we're actually seeing overall Australian temperature records, heat records being broken more quickly, much more quickly than we're seeing cold temperature records. As the average background temperature warms up slowly, you don't stop getting cold temperature records. You just get less and less of them over time. And we're actually seeing heat records being broken for maximum temperatures about 3 times more quickly than cold maximum temperature records occurring. And for minimum temperatures, we're seeing minimum temperature records, hot temperature records occurring about 5 or 6 times more quickly than cold temperature records. So we're seeing nighttime temperature records being broken and seeing changes in nighttime heat extremes even more quickly than daytime temperatures. And that has impacts on heat wave events. We don't see that cooling off at night time as much as we may have a few decades ago. And I think it's important to recognise the last 5 years we've actually seen some really significant heat wave events across Australia and in South Australia and for Adelaide as well. People may remember the March 2008 heat event, 15 days in a row over 35 for Adelaide, near record for a capital city in Australia in terms of runs of 35-degree days. And then we went on to actually have the second longest heat wave event in January-February 2009 for Adelaide. But in terms of intensity, it was actually a more significant, more intense extreme heat wave event in 2009. We actually had a really significant heat event in November 2009, which did impact crops in South Australia, across other parts of Australia. And then, of course, we've had the last few months, we've actually had a series of really significant heat events extending from about September, November last year and through early December and then the first few weeks of January, and then once again we had another significant heat event, not quite as extreme as 2008, another significant heat event just in the last couple of weeks.